Welcome to the Deep Dive. Today we are tackling, well, one of the most frustrating, persistent tensions in high-performance computing in the data science. It's this huge gap, this chasm, separating the theoretical ratio gains you see promised by, cutting-edge modeling, often using machine learning.
Right, the really high compression stuff.
Exactly. Separating that from the hard, practical demands of production. We're talking throughput, gigabytes per second.
Yeah, the stuff that actually has to run.
So we're diving deep into OpenZL today. It's a system proposing a really new framework, they call it the graph model, aiming to finally bridge that gap.
And not just by tweaking things.
No, it's pitched as an architectural paradigm shift. Now, we know you, our listeners, you're deeply familiar with the landscape, LZ variants, neural nets, all that, so we're skipping the 101.
Good.
Our mission is to jump right into how OpenZL's graph architecture aims to overcome those friction points that, well, have historically sunk even really promising custom compressors.
And that tension you mentioned, it's absolutely the defining problem right now. On one hand, yeah, you have these powerful predictive methods, often deep learning-based.
It's phenomenal ratios.
Phenomenal ratios sometimes. They model input distributions in really complex ways. But the cost, it's often extreme.
Like how extreme?
They're talking throughputs often down around maybe 1 kilobyte per second, sometimes needing heavy GPUs, massive memory. They're ratio kings, sure, but throughput poppers.
Okay, so unusable for most real-time stuff.
Pretty much. On the other side, you've got production systems. Think internet infrastructure, big data warehouses. They need stability, predictable latency, and speed. Blazing speed.
Which is why Z-standard is everywhere.
Exactly. LZ77 variants, especially Z-standard, they completely dominate. ZST compresses around, say, 100 megs a second, maybe more. But crucially, decompression often screams past a gigabyte per second.
Wow.
For high-volume, latency-sensitive work, those ML approaches, they just can't compete operationally. They get used for archives, maybe some niche offline tasks, but not the hot path.
So the natural engineering response has always been customization, right? Build something bespoke. Every data engineer knows, if you know anything about your data structure,
Anything at all.
you can usually beat the generic systems on size and speed. But hang on, you just painted a picture of huge risks with custom stuff.
Yes.
Years of development, security holes, fragile wire formats.
Right.
Shouldn't engineers just take the Z-standard hit, ratio-wise, if the alternative's all that operational pain? Why is bespoke still the natural response?
That's the multi-million-dollar question, maybe billion-dollars. They persist because the economics for massive data processors like Meta, where this research comes from, are brutal.
Okay.
Even a tiny percentage gain in ratio translates into petabytes of storage saved. Huge cuts in network traffic, I/O latency. This hits core metrics like GPU use, network costs, especially in AI.
So the savings are just too big to ignore, even with the pain.
The savings can be astronomical, but OpenZL argues the pain isn't just bad luck or bad implementation, it's fundamentally architectural. The paper specifically calls out things like deployment friction, that lagging hosts problem, where you can't deploy a new compressor because some readers haven't updated yet.
Yeah, that kills innovation speed.
Exactly. OpenZL aims to fix the ratio problem and that architectural deployment problem at the same time.
And the proposed fix, the core mechanism, is this graph model of compression.
Yeah.
So our mission today, unpack this theory, look at the implementation, analyze the evidence, and see if OpenZL really could be a new standard.
Right.
A maintainable, scalable, and high-performance standard.
Okay, so the main theoretical idea, the real heart of it, is defining the compressor itself as a compression graph. It's modeled directly on computational graphs, which you see a lot in ML frameworks. It's a directed acyclic graph, a diagram. But here, the nodes are modular codecs.
So the graph is the compressor structure.
Precisely. It's not just a diagram. It is the organized process for compression and decompression. The nodes are codecs, defined as multivariate functions, the edges. They show the data flow messages coming out of one codec feeding into another.
Let's dig into that codec definition, definition 3.2 in the paper.
Yeah, it's key. A codec is a tuple. An encoder maps inputs dollar to outputs $. A decoder dollar maps outputs dollar back to, hopefully, the original inputs operand. Well, the crucial requirement for lossless compression is strict invertibility. All are ordered tuples of non-empty input-output domains. And the rule is the output domain must be identical to the input allers, and for all inputs, applying the decoder to the encoded output must give you back the original equivni equiv.
Okay, perfect reconstruction. And this whole thing hinges on not just treating data as bits, right? That's where message sets come in, definition 3.1.
Exactly. This is a shift. Instead of thinking about the universe of all possible bit strings, a message set is a specific non-empty subset, and belonging to that set imposes semantic requirements. Meaning it's not just raw bytes anymore. A message set might require, say, that the bit length is always divisible by 64. That tells you immediately you're dealing with 64-bit integer arrays.
Ah, okay, adds meaning.
Or maybe it requires the message to be a sorted run of bytes or valid UTF-8 strings. This abstraction, moving from opaque bytes by dollars to semantically constrained messages, is where the efficiency gains really come from. It allows composing codecs based on the meaning of the data.
Not just its pattern.
Exactly. And that semantic control dictates the structure of the compression graph itself. Definition 3.3, it's a DAG. Each node dollars has its codec sieve-up dollar vels. But the edges, $1 right arrow var, they're the composition magic.
Doubly labeled, the paper said.
Doubly labeled. They specify which output stream from the source node dollar connects to which input stream the target node vide.
And there's a constraint.
A crucial one, semantic matching. The output set from the source must be a subset of the input set the target expects. This guarantees the next codec gets data it actually understands and can process.
Okay, and because it's a DEG?
It has that vital property. You can always find a topological sort. Meaning, once the graph structure is fixed, the whole decompression procedure is uniquely determined, step by step. No ambiguity.
Right.
This fixed procedural nature is what enables the universal decoder. The decoder doesn't need to know which specific algorithms were used inside the codecs. It just needs the compressed data and the graph structure itself, which travels with the data.
Okay, let's unpack the implication there. You mentioned lagging hosts before. In old school monolithic compression, if I improve my compression strategy.
You usually break the format.
Right. I need a new decoder. And I can't deploy my better compressor until every single machine that might read the data
has updated its decoder binary, which can take months or longer in large fleets.
It's a massive operational break.
A huge break. And this universal decoder framework, that's the breakthrough. Because the final resolved graph completely specifies reconstruction, the decoder itself can be immutable. The logic doesn't change.
Even if the compression strategy changes all the time.
Exactly. Writers can deploy a new optimized graph config instantly. The immutable decoders just read the new graph structure from the frame it's self-describing and follow the steps. Deployment lag. Gone.
Okay, that's a big deal operationally. Let's make the composition concrete. The tokenized codec example, figures 1 and 2, how does that show specialization?
Right, good example. Imagine you have a stream, maybe log data, lots of repeated strings like user IDs or event names.
Okay.
The tokenized codec takes this single string Minot and does classic dictionary substitution. Find unique strings, replace occurrences with indices, but crucially, it outputs two separate messages.
One.
Two. First, alpha, which is the list of unique tokens, the dictionary itself. Second, nunuvin, which is the sequence of integer indices saying where each token appeared. This is the branching point.
Semantic branching.
Exactly. Before this node, one stream, mixed data. After, two streams, totally different semantics. Alpha, the dictionary, is still basically text data. It might have internal patterns, repeats, perfect for an LZ77 variant, right?
Yeah, LZ loves string redundancy.
But not that. That's now a clean sequence of fixed width integers. Indices. This stream is ripe for completely different techniques. Maybe delta coding if the indices tend to increase.
If it's sequential data.
Yeah. Then follow up with a strong entropy coder like Huffman or arithmetic coding, which are great on integer sequences. This ability to branch off, apply different specialized techniques to intermediate streams based on their meaning.
That's impossible in a standard pipeline.
Utterly impossible if you just treat everything as bytes until the very end. The graph model changes the definition. A compressor isn't one algorithm anymore.
It's an orchestration.
A sophisticated orchestration of many simpler, trusted components. It lets domain experts build way better strategies using a library of parts.
Okay, so static graphs are powerful. But what if the best strategy depends on the input data itself? How does OpenZL handle that runtime adaptation?
Good question. That's where runtime dynamicity comes in, using the function graph, definition 3.4. Let's say $d is the set of all possible compression graphs you could build. A function graph, $5, is basically a function that maps an input dollars to a graph $d dollars. I write ROGR.
So it's like a selector.
Exactly, a sophisticated selector. It looks at the input data at runtime, maybe calculates some quick stats like sparsity or entropy.
And based on that.
It chooses and returns a specific pre-optimized graph structure from the set dollars.
So it might say, whoa, this data is 95% zeros. Forget the general LZ graph. Switch to the zero run length encoded graph we already optimized for this case.
Precisely that. And the selection process can cascade. One function graph might select another. This continues until all function graphs are resolved.
Leaving you with
the resolved graph, definition 3.5. By definition, a resolved graph contains no function graphs. It's purely standard codecs. It completely specifies the reconstruction process.
And this separation is key.
Architecturally crucial for stability. All the complex, maybe even experimental decision-making happens on the compression side.
Right.
But the decoder, it only ever sees the final fixed procedural resolved graph. That guarantees wire format stability no matter how often you update the selector logic.
Smart. Okay, let's talk implementation. How did they actually build this, the software stack?
They were very deliberate, layered choices. The core is libopenzil, written in C11.
C11, not C++.
C11 for the hot path. They chose it for maximum portability across CPUs, predictable memory behavior, super important in HPC, and easier debugging. It exposes a narrow, stable interface.
Then layers on top.
Yep, a thin C++ facade for things like RAII, better typing, and then critically, Python bindings.
For the data science world.
Exactly. Focused on zero-copy interaction, seamless integration with NumPy, PyTorch. Essential for adoption within Meta's AI stack.
And inside a codec itself, more layers.
Two main layers there, too. The actual workhorse is the kernel. Small, deterministic, allocation-free C code. This is where most CPU cycles get spent. Wrapped around that is the binding. This handles the higher-level stuff. Type checking, enforcing bounds, managing buffers. It keeps the core kernel clean and fast.
And the binding connects to OpenZL's type system.
Yeah.
Which approximates the abstract message sets.
Right. Implementing arbitrary message sets isn't really feasible, so the type system is the practical way to enforce semantic constraints.
What types do they have?
Currently 4 main ones. Bytes, just generic serial data. String sequences of byte strings, struct for fixed-size records like typed tuples.
Okay.
And numeric W, which is a special kind of struct, specifically for host endian numbers.
Yay.
8, 16, 32, or 64-bit. This focus on type fidelity is huge. It lets the compressor optimize based on knowing it has floats versus strings, like columnar database optimizations, but inside the compressor.
A byte-level compressor just wouldn't see that.
Wouldn't have a clue.
Yeah.
So deploying this dynamicity, how does that work in practice?
2 ways, mainly. First, that abstract selector function graph we talked about. Second, a more pragmatic thing. Restricted regular codec encoders. These are basically normal codecs, but with one critical rule enforced. They cannot modify the input data. They can only call other codecs, orchestrate things.
Ah, so they manage flow but don't transform. A balance between power and safety.
Exactly. And the wire format ties it all together. When you compress, you use a compressor config that targets a specific decoder profile or version, the output frame.
Yeah.
It's completely self-describing.
No side info needed.
None. It's organized into chunks you can decode independently, and each chunk starts with the full description of the resolved graph for that chunk.
The recipe determined at compression time.
Right. Followed by the actual edge payloads, the compressed data streams. Since the graph is right there, the decoder needs 0 external config files, 0 sideband info, just the frame itself. Guarantees stability.
Now, while the graph model gives you, theoretically, infinite flexibility.
Which can be daunting.
Right. In practice, the authors found that the really high-performing OpenZL compressors tended to converge on a common, structured 4-stage pattern.
Okay, what's the pattern?
Parse, group, transform, compress. They think of it logically as front-end, parse group, and back-end, transform, compress.
And the rationale?
It's sort of optimization physics. The powerful back-end stuff transforms. The final compression algorithms, they work best on clean, homogeneous, structured data streams.
But real-world input is messy.
Always messy, always heterogeneous. So the front-end's job is basically data janitor. Organize the messy input into the nice, predictable streams the back-end can really chew on effectively.
Makes sense. So stage 1, parsing. This sounds like where domain knowledge is critical.
Absolutely vital. It's maybe the biggest differentiator from generic compressors. The goal is take a flat input stream, separate it into logical semantic components. Think about a CSV file, row major.
Yeah, rows of mixed types.
Parsing would split that into multiple column major streams. all the integers together, all the strings together, timestamps together, and it discards the delimiters like commas and new lines.
It's like sorting laundry before washing.
That's a great analogy. Yeah, traditional compression tries to stuff the whole messy laundry basket into the machine at once. OpenZL's parsing stage is like a machine that first sorts shirts here, socks there, trousers over there, then applies specialized treatment to each clean pile.
How do you tell it how to parse?
Flexibly. You can write a custom parsing function and feed it to a standard dispatch codec. Or, and this is really powerful, you can use SDDL, simple data description language.
SDDL?
Yeah. You write a simple text description of your data format. SDDL compiles and runs that description, producing a stream of dispatch instructions.
And the beauty is,
as you pointed out before, this complex parsing logic only needed on the compression side. The dispatch codecs record the instructions. Here's how I split it up in their output. The universal decoder just follows those recorded instructions to pin it back together. No need to run the complex SDDL engine on the decode side. Keeps decoding fast and simple.
nice. And this works for lots of data types.
Yeah, they show examples across the board. Vector data, like PyTorch tensors. Parse separates the numbers from the metadata. Tabular data, columns get split. Complex trees like thrift or protobuf. Every unique path in the tree can become its own stream.
Okay, but sometimes parsing might go too far, make streams too small.
That can happen. You might maximize correlations within a column, but lose useful correlations between columns if you split everything too finely. That's where the grouping stage comes in.
Okay, what does it do?
It uses a clustering graph and a trainer. It looks for hidden correlations between the streams that parsing just created. If it finds useful groupings, it merges streams back together, maybe concatenating them, maybe interleaving them to optimize the input for the final compression stage. It's like a post-parsing tune-up.
Which leads to the transformation stage.
Right, and this is where domain expertise really pays off again, applying smart, reversible transformations to make the data easier to compress. Classic one is the delta codec. If you have sorted or sequential integers, replace them with the difference from the previous one. Drastically cuts down the range and variance.
Makes it more compressible.
Much more. Or parcent, which turns ASCII number strings into compact binary numbers. Or more advanced things like linear predictors. The interesting thing is, choosing the right transform often makes the data both smaller, better ratio, and faster to process downstream.
It reinforces that core idea again. Understanding structure beats brute force.
Absolutely. The efficiency you gain by transforming the structure totally outweighs the cost of doing the transform.
Okay, finally, the compression stage.
Yep. After all that parsing, grouping, transforming, the data streams are hopefully clean, homogeneous, and ready for the heavy hitters. This stage usually uses generic backend codecs.
Like what?
Often a good LZ variant, or a strong entropy coder like ANS or Huffman. OpenZL provides standard graphs like compress and entropy that often pick the best backend automatically.
And they showed an example of extending LZ itself.
Yeah, the field LZ codec. This is a perfect illustration of OpenZL's power. Normal LZ works on bytes. Field gulls works on streams of struct type.
So instead of finding repeated byte sequences,
it finds repeated entire structures. If you have fixed width records or numeric arrays, matching whole records at a time is way more efficient than matching byte by byte.
That's clever. And the standard library has parts for all this.
Rich library. Appendix A lists them. Conversion tools, numeric, string, restructuring, dispatch, concat, interleave, LZ variants, field LZ, zest2d, wrapper, entropy coders, representation changers, byte unpack, parse int, and transforms, delta, tokenized transpose, zigzag.
So the upshot is building a high-performance custom compressor changes dramatically.
Yeah. Instead of months of deep, risky C coding for a monolithic thing, it becomes more like configuring and composing components from this trusted library. Much faster, much safer.
Okay, this graph model offers incredible flexibility. But that sounds like a configuration nightmare. Which codecs, which parameters, what order? How do you find the best graph?
Exactly. That combinatorial explosion is the downside of flexibility. The authors found pretty quickly that trying to configure this manually is, well, painful.
Laborious, slow,
and almost certainly suboptimal. You'll never find the best combination by hand. Plus, trying things out at runtime, way too slow for production compression.
So what's the solution?
Offline training. It's covered in section 4.6. This is crucial. You take a small but representative sample of your actual data, your corpus. You then run an automated process to explore the graph possibilities and optimize the configuration specifically for that corpus.
Like Z standard dictionary training, but for the whole graph.
Exactly. It's a generalization of that concept. The training process figures out the best structure, the best parameters, and then it spits out the result, a serialized compressor configuration. That's the optimized graph recipe. You publish that recipe, deploy it, and you're done.
How does this training actually happen, the workflow?
They have the OpenZL trainer workflow shown in Figure 5. It's basically an orchestration framework built around plugins. You give it your corpus and maybe a starting seed compressor graph. The orchestrator starts running the compression process on the corpus data, but when it hits a component in the graph that needs tuning like a grouping node or a generic compressor backend,
It pauses.
it pauses execution and calls out to a registered training plugin specifically designed for that type of component.
So specialized trainers for different parts.
Right. The plugin takes over, does local experimentation just for its component. Maybe a clustering trainer tries different ways to group columns. Maybe a parameter tuner finds the best LZ window size.
And the results.
Crucially, these trainers don't just return the single best setting. They can return multiple good options, essentially. A local Pareto frontier, trading off speed versus compression ratio for that specific component.
Okay, a set of good choices.
Then the orchestrator gets these options back from all the plugins. It uses global heuristics to look across the entire pipeline and pick the combination of local choices that yields the best overall compressor, considering the global trade-offs.
Smart composition of local optimizations. Let's highlight some key training components. The clustering trainer.
Yeah, that optimizes the grouping stage. It takes those fine-grained streams from the parser. It uses heuristic search, maybe greedy, maybe genetic algorithms guided by a cost function, usually just the final compressed size. And it figures out the best way to merge, concatenate, or interleave those streams to feed the back-end stages optimally.
Okay, then the big one, ACE.
Automatic Compressor Explorer. Yeah, this is really the heart of the back-end optimization. It tackles the transform and compress stages. ACE uses a sophisticated genetic algorithm. Its job is to explore that massive search space of possible codec combinations and parameter settings for the backend.
And its goal isn't just the single best point.
No, its explicit goal is to produce a maximally wide range of options along the entire performance frontier. It wants to map out all the best possible speed ratio trade-offs the architecture can achieve for that data. Give the user the whole curve.
Very comprehensive. And finally, ML selector training. That handles the dynamic function graph part.
Right. How does the function graph learn which static graph to pick for a given input? ML selector training frames this as a standard machine learning classification problem.
Okay.
The trainer extracts statistical features from samples in the corpus, things like variance, sparsity estimates, maybe data type distributions. It uses these features to train a classifier model.
And at compression time.
During actual compression, the ML selector quickly calculates those same features for the incoming data, feeds them to the trained model, and the model instantly predicts which pre-trained resolved graph is likely to be best for this specific piece of data. It automates the adaptation.
All right, let's get to the results. Does this complex system actually deliver in practice? Section 6, the benchmarks.
Yeah, this is where the validation comes in. They ran trained OpenZL against a suite of strong competitors. XC for iRatio, ZOCD for speed, gzip baseline, BLOST with its btune optimizer for numeric data, and default Parquet compression.
And the data.
Very diverse real-world stuff. Huge U.S. Census CSV files, notoriously tricky, complex scientific climate data in GI format, and canonicalized Parquet data from finance and logistics domains. They use single-threaded compression for fair comparisons.
Okay, and the key finding, Table 3.
It's pretty striking. Trained OpenZL achieved the best compression ratio, period. In every single case they tested, it consistently beat even the highest setting of X-ray XZ9.
Wow. Okay, so the structured type-aware approach pays off on ratio.
Definitely confirms that part of the theory. Decomposing based on structure yields better results than monolithic approaches, even aggressive ones.
But what about speed? That's the other half of the promise.
And this is where it gets really interesting. The speed metrics show it's not just tweaking the ratio dial, it's often changing the entire performance profile.
Example.
Look at the PPMF person dataset. It's one of the biggest CSVs they tested. The trained OpenZL graph got 55% better ratio than XC9.
Okay, significantly smaller.
While compressing 11 times faster.
Wait, say that again? Better ratio and 11x faster compression than the high ratio standard.
Yep. That's not a trade-off, right? That's just
Yep.
better. Strictly dominating.
Wow. CSV parsing is supposed to be expensive. How do they get that speed and beat XC9's ratio?
Well, the paper suggests two main reasons. First, the sheer efficiency gain from the structural decomposition and specialized backend processing is so large, it simply overcomes the parsing overhead for data like this.
The back end gets easier data to work on.
Much easier. Second, those backend codecs, operating on clean, typed streams, run incredibly fast. They avoid expensive byte scanning for redundancy. They're doing targeted, fast transforms on known data types.
Any other examples of BD standards on both fronts?
Yeah, they mentioned specific time series datasets, Era 5 pressure and Era 5 wind. On those, trained OpenZL actually beat Z standard on both compression speed and decompression speed,
Beat ZST on speed.
while doubling the compression ratio compared to Z standard. Now, for data that needs less parsing, like preprocessed Parquet, they report OpenZL speeds were competitive with ZSTD right out of the gate.
Okay, so the performance profile is really strong. What about deployment? Are these trained configs huge and complex?
That's another interesting point. Table 4 shows the size of the serialized compressor configs the recipes. They're remarkably small,
Like how small?
often well under 45 kilobytes, even for those complex census datasets that needed specialized column clustering instructions. Some were less than 15 KOB.
Tiny. So easily publishable, easily managed.
Proves that concept. They can travel with the data or be managed centrally without much overhead.
And the Pareto frontier graph, figure 7.
That visualizes the trade-off landscape. And yeah, OpenZL's curve for ratio versus speed consistently sits above the curves for traditional compressors like ZST or XE. It strictly dominates. Meaning whereas ZSD or XE give you discrete levels like Magadish 1 to Magadish 9, forcing you to pick one point on their curve, OpenZL offers a continuous, superior frontier. You get more flexibility to pick the exact trade-off you need for your specific constraints, CPU, memory ratio target.
Although they did mention CSV parsing can be heavy for the most complex high-ratio configs.
They acknowledge that, yeah. But they also point out the architecture lets you just turn off the parsing stage if pure speed is all you care about for a specific use case. It's configurable.
Okay, but it's not magic, right? Any limitations?
Absolutely. They included the NWIC 7 case study specifically to show this. NWIC 7 is standard English text benchmark data.
Right.
OpenZL currently lacks specialized codecs for natural language processing. So for NWIC 7, it basically defaulted to using its generic ZIS-TD6 component. And the performance, pretty poor compared to compressors like X that are highly specialized for English text.
So the conclusion there is?
OpenZL isn't a silver bullet for all data types out of the box. Its success hinges entirely on having or building specialized codecs and configurations that exploit the specific structure of your data. It needs that domain investment to shine everywhere.
Makes sense. The proof is in the pudding, though. Did Meta actually use this internally, Section 7?
Yes, and extensively. This wasn't just a lab experiment. They report significant internal Meta deployments. OpenZL replaced a lot of Z standard usage.
Examples of impact.
Integrating it into Nimble, their columnar database, gave an immediate 10% size reduction just by letting OpenZL understand and process the numeric types better.
Just by adding type awareness.
Basically. For Scribe, their massive log aggregation system, they set up regular automated training runs. This maintained a consistent 15% ratio improvement over optimized ZSTD, adapting as log formats evolved.
And the impact on AI workloads. PyTorch.
That was significant. PyTorch modeled checkpoints huge tensors saw an average 17% storage saving. Why? Because OpenZL could leverage the type information. Floats, integers. This directly cut network traffic, reduced I/O load, and ultimately helped GPU utilization during training.
Non-trivial savings at metascale.
Absolutely. Another log aggregator saved 18% by ditching inefficient serialization. They just sent typed integer arrays directly to OpenZL. And crucially, because of the modularity, when they needed new custom codecs, like for bfloat 16 embeddings, common in AI, the development time was apparently reduced to days, not months, because they could reuse existing components.
How did they manage deploying all these custom graphs?
They leveraged Meta's existing managed compression system. This was originally built for distributing Z-standard dictionaries. They adapted it to handle the whole OpenZL workflow, training, validating the generated graphs, serializing them, and pushing the configs out to thousands of machines.
So the operational complexity, while higher than just using ZSE level 3, was manageable at enterprise scale with the right automation.
Exactly. It proved the architecture could be productionized effectively. Outro.
Okay, let's try to synthesize this. The big takeaway seems to be that OpenZL powerfully demonstrates a principle: the efficiency you unlock by deeply understanding and exploiting your data structure.
Using that graph model.
Using the graph model, it just dramatically outweighs the computational cost of doing the parsing, the grouping, the training,
By enabling this composition of small, specialized, vetted codecs,
instead of one big algorithm.
the system delivers both superior ratio and superior speed, effectively pushing out the entire performance frontier compared to traditional methods. Yeah, and I think the core architectural advance, the really clever bit, is that decoupling. Separating the compression strategy, which is the graph config, decided dynamically at compression time from the fixed, immutable decoding mechanism, the universal decoder.
Right.
That structure guarantees the wire format stability, solving that lagging host nightmare, while still allowing really rapid innovation and optimization on the compression side through that automated training.
The authors themselves mentioned the unreasonable effectiveness they found when they first started applying automated training tools like ACE and the ML selector to this problem.
Right. It works surprisingly well early on.
So given that the graph model provides this seemingly ideal modular structure for composing simple functions, here's a final thought for you, our listeners, to chew on.
Is the future of compression actually less about searching for the next big monolithic algorithm that tries to handle all raw bytes universally? And is it maybe entirely about developing the next generation of meta-learning systems? Systems smart enough to automatically generate the optimal, component-based, domain-specific compression graph for any given data type.